From your music playlist to your search results, there are these invisible engines called sorting algorithms working tirelessly behind the scenes, just organizing our digital lives. But have you ever wondered how they actually work? Well, let's dive in and take a look.
Okay, picture this. You're shopping online and you click sort by price, low to high. In that tiny fraction of a second, your computer solves this classic puzzle, how to get a whole mess of items into the right order. But how does it decide the best way to do it? That's what we're going to unpack.
All right, we're going to start with one of the most straightforward methods out there, selection sort. Seriously, if you had to sort a list of numbers from scratch with no instructions, you might actually come up with this yourself. It's that intuitive. The logic here is just brilliantly simple. The algorithm scans the entire list to find the absolute smallest thing and then swaps it into the very first position. Okay, that spot's done. Then it just ignores that first item, scans the rest of the list for the next smallest item, and swaps it into the second position. It just keeps doing this, shrinking the part of the list it has to worry about until there's nothing left to sort.
Think about it like you're organizing a messy bookshelf. First, you'd scan that whole shelf to find the book that comes first alphabetically. Let's say an author whose name starts with A. You grab it, you put it in the first slot. Now that slot is locked in. Then you scan the rest of the shelf for the next book in line, maybe one starting with B, and put it in the second slot. You just keep going like that until every single book is in its final sorted place.
But how does it perform? This is where we see its big weakness. Because it has to scan the remaining list for each and every slot it needs to fill, its performance is what we call theta n squared. Now that's just a fancy way of saying if you double the number of items, the work required actually quadruples. For a small list, it's fine. But for thousands or millions of items, it becomes incredibly, painfully slow.
So that inefficiency is obviously a huge problem for big lists. The question is, can we do better? Oh, absolutely. Let's look at a bit of a smarter approach. Insertion sort.
Insertion sort works a little differently. It builds up a sorted section of the list, one piece at a time. It takes an item from the unsorted part and then finds its correct position within the part that's already sorted. It's kind of like how you might sort a hand of playing cards as you're dealt.
Let's go back to our shelf for a second. Imagine a small section is already perfectly sorted. You pick up the next unsorted book, and you compare it backwards with the sorted ones, shifting each later book to the right to make a little space. As soon as you find the correct spot, boom, you slide it right in.
Now here's where insertion sort gets really interesting. In a worst-case scenario, like a list that's completely backwards, it's still slow, theta n squared again. But, and this is a big but, if the list is already almost sorted, it is lightning fast. We're talking theta n. This makes it perfect for situations where you're just adding a few new items to a list that's already in order.
But what if you've got a massive, completely random list? Both of our simple sorts really struggle. To handle this, we need a totally different strategy, a really powerful paradigm in computer science known as divide and conquer.
The idea is simple, but it is so powerful. First, you divide the big problem into smaller, identical little problems. Then you conquer each of those little problems, often by just dividing them again and again until they're so tiny they're trivial to solve. That's the recursive part. Finally, you combine all those little solved pieces back together to get your final answer.
And the first algorithm we're going to look at that uses this exact strategy is called merge sort. It takes that divide and conquer philosophy and just applies it directly to sorting. Merge sort starts by literally tearing the list apart. It splits a list in half, then it splits those halves in half, and it just keeps on going until it's left with a whole bunch of tiny little lists, each with only one item. And hey, a list of one is already sorted, right? Then the magic happens. It starts merging those tiny lists back together, two at a time, putting them in the correct order as it goes. This continues until everything is merged back into one single, perfectly sorted list. And this right here, this is a huge leap in efficiency. Merge sort runs in what's called theta n log n time. All you really need to know is that it's way faster than n squared for large data sets, and it's consistently fast no matter how messy the initial data is. So what's the trade-off? Memory. It needs extra space to hold those sorted sublists while it's merging. This means it doesn't sort in place. It can't just do all the work within the original list's memory space.
So if merge sort is so reliable, why isn't it the only algorithm anyone ever uses? Well, because in the real world, another algorithm is often even faster. Let's meet our final contender, quicksort.
Quicksort also uses divide and conquer, but it goes about it in a totally different way. It starts by picking one element from the list, any element, and calls it the pivot. Then, it rearranges the entire list so that all the elements that are smaller than the pivot are on one side, and all the elements that are larger are on the other.
After that, it just applies the exact same logic recursively to the two new sublists. Now, on average, this is extremely fast, theta n log n, just like merge sort, but with the awesome advantage of using no extra memory. But, and here's the big catch, its performance completely depends on picking a good pivot. A bad choice can cause a total meltdown, making quicksort just as slow as our simplest, most basic algorithms.
So we've looked at 4 really different ways to do the same thing, and each one has its own strengths and weaknesses. So which one is the champion? Which one wins? Well, let's put them all side by side.
This table really lays it all out. And what you see is, there is no single best algorithm. It all depends. If you just need something simple, you go with selection sort. If you know your data is nearly sorted already, insertion sort is your hero. If you need guaranteed speed and you can spare some memory, merge sort is your reliable workhorse. And if you want the fastest average speed and you're willing to roll the dice on a rare worst-case scenario, quicksort is the top performer.
So the right choice always depends on the situation. And that leads us to the final, really critical question. Knowing all of these trade-offs, how do the systems we use every single day actually make this choice? Well, a lot of the time the answer is they don't pick just one. They use these clever hybrid approaches that combine the best of all of these algorithms to get performance that's even better.
And that's a quick look at the logic behind how our digital world gets so perfectly organized. If you enjoyed this breakdown, make sure to like, share, and subscribe for more explainers that look under the hood of the tech we use every day. Thanks for watching.